Hey everyone. So we'll start the talk today. So today we have Aditya Kusupati to give us a talk. Aditya is currently a staff research scientist at Google DeepMind. Previously, he got his PhD from UW and he did his BTech from IIT Bombay. So he was my senior and I quite know him personally. Um, Between his BTech and PhD, he also was a research fellow at Microsoft Research and he's done great works in and his research interest generally is in next generation machine learning geared towards more adaptive intelligence. So today he'll give us a talk on his research and yeah, I'll hand him the floor. Yeah, let's welcome him.
Thanks so much. Yeah, hi all. Yeah, it's nice to be here. San Francisco has been pretty cold in the last couple of years. It's like I'm still in Celsius. It's like 11 Celsius. It's
Oh, wow.
pretty bad. So, anyway, so yeah, I mean, usually when I give this talk, it's a bit more overarching and philosophical. It's just one simple technique on how you can scale things up. So feel free to stop me at any point of time. You have any questions? There are three logical breakpoints in the talk. You can stop me at that. Like we can take questions, go deeper depending on what you think, sir. But yeah, at high level, I'll be talking about the notion of Matryoshka. Matryoshka stands for the Russian nested doll, and it's a doll within a doll within a doll. And how this simple principle can be applicable to any fundamental machine learning building block we have, even up to the largest of the language models. Okay. A lot of this work was done during my PhD. I was also a part-time student researcher at Google back in the day, so I continued some of the line of the work even after I joined full time in the last year. Okay, so at a high level, I use this word adaptive intelligence, and what I mean by adaptivity and why do we need adaptivity is every single deployment setup and even training setup is ever changing, and a lot of the things which we train today might not actually cater to things in the future. It could be data distributions, it could be compute, it could be deployment hardware, etc. So when we usually design these systems, the largest of the machine learning systems, we often assume that like something is going to be working well for a long time, and the rigid design is kind of good enough for a lot of use cases, but not great for every use case. In this talk, I want to change the thinking around this by proposing introducing adaptivity or elasticity as a first-class citizen into each of the fundamental ML blocks, such that when you build any existing system, the same system just can completely adapt itself for changing scenarios without you having to intervene during the deployment stage. Okay. So that's the overarching goal, and we'll be working towards that, starting with vector representations. So just plain old vector representations, which are real numbers. So usually when I started my PhD, I was training ResNets, a lot of ResNets. And yeah, we used to give in an image. Image encoder can be a VIT or a ResNet. Used to give us a d-dimensional representation. We used to call them representations used for transfer learning, embeddings, whatever you want to call. In ResNet 50, it's 2048 usually. However, for the case of this talk, we'll use 128 dimensions as the leading example. And you used to take this embedding and you used to do a lot of downstream tasks. We used to freeze this network and say that this embedding has a lot of information about this data point, which is a dog, and I'm going to build my systems on top of it. It could be segmentation systems, detection systems, search, or classification, anything. However, some of these downstream tasks are latency sensitive, like something like search. If you go to like tens of billions of documents, you need sub-millisecond latency, and your search cost scales directly in proportion to the dimensionality of your embedding. There is no getting around it. If you want to do anything fancier, you have to compress it post hoc, and you start losing performance. On the other hand, you also use this fundamental representations for more accuracy sensitive tasks like segmentation and classification. So there could be a classification task, which when you go from 128 dimensions to 64 dimensions, loses like 3% in accuracy, and it is very crucial 3%. And your search actually cuts down latency in half for similar recall. When you start going into deployment settings, usually it's search which wins over, and you're going to be stuck with a 64-dimensional classification, losing out that 2% which you would have gotten if you were able to deploy a 128 dimension. And because more and more you want universal representations for a given data point, you want only one of this encoder capture all the information you need for all the tasks. So you'll only be having one such encoder anywhere on your device or your service. So my claim is that having this trade-off is neither accurate for the things which need to be accurate, nor adaptive because it cannot cater to both the solutions at the same time. Okay. So to fix this, we introduce this simple concept called Matryoshka vector representation, where we'll get the same vector embedding, but we are now going to reorder the information such that the most important information is in the first 16 dimensions. Okay. And the next important information will be the first 32 dimensions, which already have the first 16 as part of it, which is the nesting in the 32 dimensions. Same with 64. 64 has the first 32 dimensions to be the same as 32 dimensions. 16 will be the same as 16, and so on. You go to 120. And you can use this varying dimensionalities, which look like the Russian nested dolls, as a proxy for understanding how much information we are storing. So the smallest doll can help you identify what kind of a doll it is, high-level features. And the largest doll has all the semantic information you need to perfectly reconstruct. So in short, when you have this vector representation and you have a latency sensitive such task like retrieval or search, you just slice the first 32 dimensions and use the first 32 dimensions for all of your search. And you can use your 120 dimensions for all of your classification. Okay. And I'm going to show with some results that this is accurate and adaptive enough to solve the setting I initially proposed. So a question people ask me is, how do you reorder this information? Is it like extremely complicated? Are you going to do some fancy math to ensure that the most important information is reordered? Turns out answer is no. It's an extremely simple loss function. Whatever your representation learning function is, your classification, contrastive learning, next word prediction, it doesn't matter. You take the same loss, apply it at 128 dimensions, apply it at 64, 32, and 60. Okay. One thing you want to know is if you do it the other way around, from 16, 32, 64, 128, all of the compute is reusable because the 16 dimensions is nested in 32. So all of your loss computation of 16 goes into the 32. And you just add up all the losses, you join it. This training has no additional training overhead if you do it right. And it is as cheap as training 128 dimensions. However, you get all of these nestings in one solution. So at a high level, what is happening here is your 16 dimensions is getting 4 times more gradients than your 128 dimensions. So that forces the model to learn the most important information to be in the first 16 dimensions because the loss has to do that. If there's no other way it can do it. And the generalization of this would be you can reweight the losses based on what you want, but usually full weighting works. So we call this paradigm Matryoshka representation learning. And in short, it is basically solving the same learning task. It doesn't matter what the learning task is, what the data is, what your modeling is. We'll say do the same learning task at exponentially separated granularities like 128, 64, 32, 60. And that's pretty much it. That's the whole of training algorithm. And what comes out of this is, if you want to visualize it in terms of data, is the 16 dimensions has a very, very, very coarse representation of a dog. It can only define between a dog and a cat. Here, its superclass accuracies are pretty good, but its fine-grained accuracy starts to fall off a cliff. It improves as you go along, and at 128 dimensions, if you actually fit a good enough decoder, you can perfectly reconstruct the dog. Okay. Yeah.
I guess in these like one-dimensional representations, when you're cutting up, like would these not be, is there not the risk that maybe like, I guess some like rotational element where it's there is smaller dimensional representation, but that it's maybe not like just 16 of the 128 parameters, but rather like, I don't know, like a rotation in which it's using more for like more of the values, but
that's a good question. So if I were to rephrase this, you're asking if I take the 128 dimensions and do some sort of projection, can I do better than this 60 dimensions? Yeah. It turns out, I'll come to that in a minute.
Okay.
This 16 dimension is usually the best you can train. And if you add a PCA on top of this 128 dimensions, your trivial solution will be a 16 dimensions, rotation will be. And then if there is any additional information you can pack into 16, you can. But your 16 is going to be extremely strong. I'll show the results in a minute, but that's a good question. If you actually look at it, this is a nonlinear PCA, and with enough data, in a convex case, this will be the best possible solution. Okay. And because everything else will be noise as you go. Yeah.
I was curious.
I didn't get you. This is exponential split.
Like, so, it's like random.
No. So okay. So when you do any of the training in machine learning, you see that the training is log linear. So if you double something, your accuracy goes linearly up. So you can choose to do 128, 96, 64, and so on, but you're not going to add any more value than what you're doing right now. I'll show it in a minute, but this is something I initially tried. We have a revelation in the paper where we try to update on other strategies, including random. But it turns out log, like the exponential separation, is very, very strong of a design choice that just like solves most of the things we care.
I think the question was also like, what embeddings do you think for the lower dimensionality? Like, keep the most of them.
Okay. The dimensionality of the lowest embedding. That's okay.
Like what feature? I think that's for the question.
Yeah, how do you choose?
It's like if it's a 128 vector, I think they're just asking what 16 dimensions do you think? I think it's just first 16, right?
Yeah, we just always pick the first 16.
Yeah, I think that's what they're asking. Like when you say 16, is it 16 random numbers from 128 or
Okay.
the first 16? I think that's
So when we are learning this, the 128 dimensions is now all ordered. So when we say the best 16, it's always going to be the first 16. When we say 32, it's going to be first 32, which already has the first 16 as part of it. It's not required for it to be ordered. You can actually on the fly choose, like, I want to do second index, 18th index, 20th index, but whatever you pick during your training is what you want to use. And if I understand the other part of the question, there is no enforcement of what features we are trying to make it learn. We just are seeing what the data will help it learn. And last part of your question is how small of a dimension it can go to. For vision tasks, we show that it can go up to 8. For language, we have successfully done until 48, but anything below that, it's a bit destabilizing.
If you have more separations, does that improve the performance? Like in this case, you have, I think, the 4 separations. You have like 5 or 10 separations or something like that. Or like not even necessarily exponentially spaced, but like you just have 5 separations. Does that do better?
That's a good question. It's the same. Initially, what I thought was the question was, we did ablations. It turns out this is as good as anything else, and this is probably the cheapest way to do it with the least number of partitions. I'll show the results in a minute, but
is like increasing the number of partitions, like in a
usually
given like
doesn't.
range?
I mean, you can think that there is additional gradients, but it turns out after a point it gets saturated. So there is a roof line. We can't cross the roof line. Any other questions? Okay. So yeah, I mean, we do this, and a quick way of testing out a bunch of the questions you guys are asking is, I'm going to train 9 different models for 9 different representation sizes. So 8 dimension, 16, 32, 64, and so on up to 2048 on the same data. And I'm going to evaluate with one nearest neighbor accuracy. One nearest neighbor is, I'm going to encode all of my image in a train set. My test set comes out. Whenever an image comes in, I go and like pick up the closest nearest neighbor in the train set, see what the label is, assign it as a label. There's also a proxy which you can just do with your linear classification, linear probe. However, this is a bit more generalizable because it also applicable to search, not just the classification. So the number here is generalizable to both classification, search, as well as results. So each of the red points is independently trained. So they are like trained completely to saturation. And these are the best possible numbers you can get if you were to train an 8-dimensional embedding from scratch on this data with this architecture. And if you take the largest 2048 dimension and add a projection on top of it, some sort of rotation, some sort of SVD PCA, it holds up accuracy quite well until 128 dimensions, and then it falls off. So a linear-ish transformation on top of this 128 dimension, 2048 dimensions, after a point cannot capture the nonlinear dependencies between all of these components. So it just falls off a cliff as you go down to lower dimensions. In contrast, the blue points you see is one Matryoshka representation learning model or MRL with the granularities of 8, 16, 32, 64, and so on to 2040. And you see this, each of them is as good, if not better than the corresponding data. Okay. And especially when you look at it, the lowest compression ratios, the accuracy increases significantly compared to a baseline model. One way of thinking about this is training an 8-dimensional model is extremely hard because it's a very small information bottleneck. Adding these additional parameters helps it have over parameterization, which makes your optimization a bit easier. And it helps optimization a lot more along with extra gradients, so the accuracy improves. Okay. So in short, like if you add anything more as well, any other granularities, often we don't cross anything beyond this, and all of them fall on the same line. And the red one is a good enough proxy for you to know that that's your Pareto, and like if you're improving slightly on top of it, that's already hitting. Right. And the most interesting experiment in this paper for me is granular interpolation. What I mean by that is I trained for 8, 32, 16, whatever I did 2048. But someone comes to me and says, hey, I want to deploy a search system with 48 dimensions. What do I do right now? And this answers to your question as well, like, do you need like more granularities to train if someone wants 48 dimensions? The answer turns out to be no. You can literally take the first 48 dimensions and it falls on the curve. And it's as good as a 48 dimensional baseline you can ever train. So it has a smooth interpolation. So the way you want to think about it is the 32 dimensions gives you an accuracy. Then the next 16 dimensions gives you the half of the marginal accuracy on whatever the 64 can give you. So it just smoothly interpolates. And just a second. On top of that, if you actually add a rotation matrix, if there is something additional, you can slightly push this even more, but it will still be very, very close to the Pareto. Yeah, first time.
Okay.
You asked.
Yeah. I've always been curious about this in the sense that you've never trained, like when you're adding the next 32 dimensions, you don't train the next 32 dimensions to be in the same order. The only training that you're doing is like, the first 16 should be better than the next 16. So do you have an intuition of why like it's such a smooth interpolation where you're just saying taking the next 16 and it still works fine?
So there is a very nice paper in 2018 where, again, it's stretching it, it's a theoretical paper, but it's pretty nice. Is they show that SGD actually forces diffusion of information across all the dimensions you have. So there is no statistically significant way of picking the best n dimensions
I see.
across a huge portion of data. So the data will pick different sets of n dimensions. So if I'm not optimizing for the next 60, any 8 is as good as any 8. So, yeah.
Yeah, I think that's my clarification question. So it wouldn't matter whether you take the next 60 or in any of that new chunk, let's say.
Yeah.
You could just randomly take it.
So does anyone want to answer why the ordering is cleaner from a systems perspective? Yeah.
Like hash hits and stuff.
Perfect, right? Like you can page things such that every single column is in there, and you can compute stuff with 16 dimensions. Whatever is your top candidates, you can only fetch the next 16 for the other things, and so on and so forth. So it's so perfect that you can just like build a database with like chunks which are columnized, and you don't need to ever cache in anything beyond 256 unless like it's an extremely long tail list. Any questions? I mean, like this is as simple as it is. Like this is the whole of the research. It's 4 lines of code. You guys can go and implement it. You're not even getting exactly 4 lines. It's a for loop.
I guess my question is sort of like the reverse of my last question, which is how could you get the number of partitions such that you get this effect?
Still exponential, I would say.
So this is like the optimal, like,
This is the first experiment I ran. That was the right experiment. I didn't bother to figure it out. I had 2 GPUs back in the day, okay? Like, let me run whatever. But it's good. I mean, like, we actually tried to prove that like something can be better, but so if you know the lowest you want, let's say like 8 might not be something you care about. So 32. You just start at 32, largest you have, you extrapolate, interpolate based on whatever you can. If it is not a perfect power of 2, go to the closest one and add the additional stuff. Any questions? Yeah, you can do more tricks on this, like model swooping works on top of this. Distillation, like self-distillation, you can distill the 128 dimensions into 16 dimensions through logics. All of these tricks work. So anything is a fair game after on top of this.
Just a clarification question, at least for these set of experiments that you have shown.
Yeah.
Is it just the initial embedding that is like in this representation format, or is it like every layer, like you're trying to do this?
That's a good question. This is only the final representation of
Okay.
any encoder.
Okay.
Like it's just the last layer. That's the reason the compute is reusable. If it is not
Okay.
the last layer, compute is not reusable.
Okay.
Okay, so it interpolates smoothly, and that's pretty much it. So the takeaway from MRL is you just need one representation for all of your use cases, and for anything, you can literally slice off the first k dimensions and use it. We scaled it to every single modality, every single model we had access to both at Google and GitHub, and any representation and setup, and it just works out of the box. And yeah, finally, it is adaptive in my definition because it helps you scale to accuracy of a task as well as latency sensitiveness.
Yeah, I think there are a couple of questions online. So, Shiching, do you want to go first and ask the question?
Yeah, sure. Thank you. So basically, I just want to ask the same questions as I put in the chat. So basically, I think this looks very exciting, and I was wondering if this can be applied to large language models with a lot of layers, and then potentially you can do the same thing for every layer. So you can have one big model that can function in its full functionality, but if you just drop some dimension at every layer, you get a smaller and more compressed model. And then you can have a similar accuracy and the parameter size curve like in that figure. I'm just wondering if that's possible. And then if we apply that to every layer, does the error propagation probably bring some issues to that? Yeah, that's my question. Thank you so much.
5 slides. This week.
Did you get the thing, Shiching?
Yeah, I'll just wait for 5 slides.
Okay.
Then you get all the answers.
Okay. Anik, do you have a question?
Yeah. Hi. I also had a question with regards to how are you? So he said like it doesn't matter whatever dimensions that you select with respect to the 16, 32, 64 from 128. But then once you select the 16, the first 16 on the next 16, how do you sort of ensure that the first 16 will be the best out of the next 32, 64? What is the loss function, that optimization that you are working on? That was my question. And once you have ensured that, how are you basically the methodology? That would be my question.
We're not picking anything. We're just saying that the first 16 are we are going to apply the same loss as 128.
Okay.
Let's take a very, very concrete use case, right? You're doing clip training with contrastive learning. Let's say your 128 dimensions is contrasting with 128 dimensions of your text embedding. I'm going to
Can you speak a little loudly?
Yeah, I mean, if you are doing a clip training, you have a 128 dimensional text encoding embedding and image embedding. You're doing contrastive loss on 128 and 128. You're also going to do the same contrastive loss on the first 64 dimensions of both embeddings. And in contrastive on first 32 and first 16. You add up all the losses and just do back propagation.
Okay. So it's basically working in parallel. It's not it has got nothing to do with let's say how you are training in 128, how you're training in 64. There is no cross correlation with it. just taking the first 16 and you're just implementing in parallel to uh, the 32, the 64, the 128, right?
No, I think there's some sort of communication gap here. The optimization is still joined because your gradients are all accumulated into the same parameters. So your 64, 128 are optimizing the same parameters, and they're optimizing for the same loss. They're trying to maximize the cosine similarity between positives and minimize the cosine similarity between negatives. And a 16 dimensions to be good has to be the first 16 dimensions of 128 to be good as well. So the loss of 128 dimensions, 64, 32, help 16 dimensions become better because otherwise the total loss is going to be very high.
Okay.
Any other questions? Okay. Okay. So I just want to, so this was done 3 years ago. It's an age in deep learning. However, the paper became popular about a year ago because every single search system currently you touch Google, OpenAI, any embedding model, Pinterest, every single dense representation is Matryoshka right now. There are about 1 billion users we are serving every single day. And like, I mean, if you are building a RAG system, you definitely have Matryoshka systems out there. If you have use search in Google, it is. Microsoft has a bunch of enterprise products which use Azure AI Search supporting OpenAI's Matryoshka. So yeah, most of the dense embeddings out there are on Matryoshka. And it's not just industry, Salesforce really liked it, and about 10% of all of Hugging Face's model downloads are Matryoshka. Any encoder model which is uploaded now by default has Matryoshka representation. This accounts for like I think nearly like 10 million downloads in the last 1.5 years or so. Yeah. It's not just output space, it's not just the representation space. People did very, very interesting things. Around the same time, we wrote the paper as well as after that. Also, I wanted to add, we were not the first people to invent this. This was first discovered in 2014 by Warren Ripple and Ryan Adams. They were doing it from a compression perspective on reconstruction and like ancient and deep learning time. The task was different, so scalability and the sensibility of applications were different. That's the only difference, but the core idea is the same one. And then people took this from input space, moved it to output space. So if you have images, you can process 14 by 14 patches, 3 by 3 patches, 16 by 16. So if you process 3 by 3 patches, you have a lot more compute. And if you have 14 by 14 patches, you have a lot less compute. So you can literally trade off the compute by changing your patch size. And this is Matryoshka in input space. Lucas Baer and co created FlexiVid based on this. And then, of course, a bunch more university folks brought this Matryoshka idea into token space of VLMs and in general, any of the models which have potential for variable length tokens. One of them is from UCLA, when Bo worked on this Matryoshka transformer. At a similar time, there was Matryoshka multimodal models, which made Lava completely adaptive. There's also work from MIT, which talks about adaptive compressibility rates and how to add extra information as you go along. You can think of this as Matryoshka, which is adding extra information as you go along. So it's the residuals which you can after that. The most surprising thing I got to know was people started leveraging Matryoshka for interpretability and mechanistic interpretability work. Apparently, sparse autoencoders have some issue of collapse in concepts. Just by adding Matryoshka, loss vanishes. Just becomes very, very good and it's very stable. So three teams independently discovered it at the same time and like they all came to the same thing. That was pretty interesting. Then more people started doing decoder diffusion style stuff, which is more unit style, where they were able to generate variable resolutions, also process variable resolutions in Matryoshka style. So this includes adaptive compression from Meta and Matryoshka diffusion model. So yeah, I mean, in short, like the idea is very general and it's not just us, but a lot of people have found value in it. So having said that, answering the most burning question, how does this apply to a transformer? Turns out transformer is just a bunch of matrix vector multiplications. So wherever you see a vector, you can put a Matryoshka there. And you add the same exponential structure of Matryoshka. Let's call it XL, L, M, and S. It can be like 128, 64, 32, and 16 for all practical purposes. And yeah, this is a single block of transformer changed into Matryoshka, and we call it a matformer block. You stack transformer blocks, it becomes transformer block model. Stack matformer blocks, it becomes matformer model. And the way you train it is very similar to Matryoshka representation learning. You stack all the layers with the smallest granularity, becomes model S. All the medium granularities becomes model M. Large to large. Same batch of data, do a forward prop, compute loss, jointly optimize. The only difference between this and Matryoshka representation learning is the compute here is not reusable because these are all non-linear networks. So you cannot use the compute of a model S to already like initialize the compute from model M. So you need to recompute it. However, because we are using the shared data and a lot of the shared computation infrastructure, optimizations all go hand in hand, training of these 4 models jointly is about 30% cheaper than training these 4 models. So if you have a llama, which is 7B, 13B, 35B, 7B, training all of them on the same set of data versus training all of them jointly, second one is going to be much cheaper than the first option. Yeah.
Is it for this is like analogous to maybe like quantization aware training where you prepare the model to be able to then in the future, like, I don't know, reducing.
The goal is similar, but it's, yeah, the parallels are a bit too fast stretched, but like the goal is.
So will you, in every single place that a vector appears in a transformer, you could just like make it?
Yes, currently just think about it from the FFN block of the transformer, but anywhere and everywhere you see a vector, you can make it Matryoshka.
So even like the key query value, yes.
Even the attention heads. Because people found the tokens can be Matryoshka, so attention heads can be Matryoshka. Any other questions? Again, like a file and for loop code change with masks. So I think complicated. Yeah. So, and then, yeah, like now you can use the smallest model for your phone, largest model for your cloud, but there exists an iPad which falls in between model L and model M. What do? Can we bring granular interpolation here? It turns out yes, but the way is a bit different. We call this mix and match. So the first layer can be a small granularity, second can be a medium, third can be a large, and so on. So you can see that if you have 4 and like 4 granularities and like 10 layers, that is the power of 4 possibilities. And most of these things, if you sample them right, fall in the Pareto of all of these other models. So you can literally sample the models during inference time, never train them, and deploy them. I'll show results in a minute, but yeah, and any questions here?
Sorry, how would the selection of how big of a embedding to use at a certain point be done?
That's a good question. So that's a heuristic. It also can be automated through search. Neural architecture search was literally built for this, but they used to train models after they found the architecture. In our case, like the models exist, you go and type with the model. So it's exactly the flip side. Like your search is going to be, and you can just take a data set, run a bunch of things, you know where to search for, and you can optimize for your search. We have heuristics which work really, really well. One thing we call it is inverted pyramid, where we start with small, medium, large, extra large, and then we go back down. That works really well. The other way, the unit style stuff also works really well. So, and then we alternate between a bunch of these things. Yeah.
For feedforward, I understand that this works, but does it also can work on tokens and embeddings as well?
Yeah.
The extension problem?
Yeah.
We don't need any projection layers, additional one.
You can just slice it off the slice is a projection, right? So slice is a projection with an identity matrix with diagonals cut off. Yeah, I mean, like slice as a projection is like very weird thing to think about. Slice is a projection.
Just a like afterthought, like how the two paradigms are different, where here you're doing mix and match. Previously you were like, we can do
You
granular.
can actually do granular interpolation here as well.
Okay,
but
yeah.
It turns out like it's not really Pareto optimal because
Okay.
the error propagates. Not
Okay.
actually as the right question, the error propagates. So you actually target for the blocks which you've trained first, so the error
Okay.
doesn't propagate as much. Like it's all like no good.
Okay.
But it's still like within the noise range of Pareto, it's not the best thing.
Okay.
Sorry, going back a few slides, in the training of these things. Like here, we're training, I guess, a very or like a very constrained model side by side with a model with a lot more expressivity or something like that. But would it not be like maybe like along the lines of like lottery ticket hypothesis or something like that? Would it not be more effective to train the bigger one and then cut down or something like that? In terms of the performance of then the smaller, like through pruning, or in terms of the performance of the smaller one?
Okay, that's a good question. So first of all, lottery ticket hypothesis is the opposite.
Hmm.
So it doesn't say you can prune something, it says that there exists a smaller model you can create from scratch.
Yeah, I guess maybe papers after lottery ticket hypothesis. that
Pruning
should-
has existed before that, but like,
Yeah.
like lottery ticket is the exact opposite of it,
Yeah.
but yeah, it's a good question, like, why don't you just prune the largest model? Yeah, I mean, I'm completely okay with that. I'm going to claim that this is as good as any model out there. It's the same argument I'm going to make with 8 dimensions. You could have pruned or like add a projection to get a best 8-dimensional model, but it turns out this. But you can also think about it, even if this is destabilizing your training, that will still have to train. So it will kind of like require this model to start doing well, otherwise the total loss will. You can prune, but the thing is pruning after you prune needs extra training, so you're not going to account for those totals.
Yeah.
It's also going to be unfair because you practically retrain that. I think. If you look at something like Llama 1B or 3B, they pruned it from 8B, but they had to retrain it on all the 15 billion tokens. So
Yeah.
then you might as well just train the model from scratch. Yes, it could have been worse than pruning one, but you might as well just visualize it.
But this training is still maybe 4x.
No, it's half, it's 1/4 size. So it's the total training will be 2x of the largest.
Yeah,
one.
I see. I see, yeah,
It's not good because that's the beauty of exponential separation.
right.
I just wanted to ask if there's any like intuition for like which sets of features appeared in each like dimensionality. Like at the beginning, you alluded to the fact that okay, the first 16 is really good superclass classification. And of course, we're adding additional detail, but have you done any? Has there been any studies on it? Like okay, we can generally see there's this curve of like so these sort of like for images, right? Like these sort of features appear in the next for like indexes after the first 16, etc.
So that's a very good question. Like in the images are easy because you can always visualize something, even if it is garbage, something is visualized. Text is a bit hard. The way we tested out what is useful and what is not is see the proportion of the tasks you can solve with the smallest model. The easier tasks are always solved by the smallest. Something which is very frequent, solved by the smallest model. Something which is not long tail, which is very frequent, solved by the smallest model. As you add more capacity, it's further longer tail. So you can solve like 80% of your tasks with the smallest model. It's the 20% that requires you to get there. Cool. So it's the same plot, 4 different models, 4 separate trainings, different accuracies. This is on VIT for encoders just to have consistency. And if you train a matformer, all of these models from a single model. And yeah, they're as good as compared. Now the kicker, all the stars are mix and match. They never trade. They're always on the trade.
We have the comparison with the baseline on quantization.
Oh, these are all complementary to quantization. So you can quantize on top of it. This is a question we were asked so many times because they asked about pruning, they asked about quantization. It's all complementary because it's just less smart. Any other questions? Okay, so the burning question, how does this work for language models, not just like VIT encoders? Turns out scaling laws are exactly overlapped. So if you train, and this doesn't account for the 100+ free mix and match models you get. If you literally like take all of the granularities, plot a scaling law, give scaling. That's good. There's no reason you should not be trained with it. The only constraint is because you have to train these 4 models, you either have to use larger number of GPU memory or you have to micro batch. So the effective cost is the same, but your one-time cost is going to be slightly more horizontal than vertical. Yeah, that's the one catch. So as someone asked, what else does this work on? It works on MLP hidden dimension, works on depth. So you can skip like middle 5 layers. You don't need to skip the last 5 layers. So Matryoshka depth. So there's also the more formal version of this is mixture of depth paper, but NVIDIA also discovered it as a mechanism, just advanced style models. You can do it in attention, and you can also do it in your embedding. That's the model. Yeah. Any questions?
I guess, yeah, what is the relationship between this and say, like dropout, which I guess,
This is nested dropout.
but so, okay, it's nested dropout and maybe more targeted dropout instead of like maybe some random proportion.
So the 2014 paper is literally called nested dropout.
If you are applying dropout to like a specific way, then would you be applying that dropout across like all 4 of those losses?
So it's the first, again, it's the same idea. The first 16 dimensions across all the layers. First 32 across all the layers.
So like, I guess my question was like, if you're implementing dropout, right? If you just have the one loss, then you just have 0 those weights for that.
Oh, we don't do dropout. We actually slice the weights so that it's faster. We don't. So in the fastest, like we literally like shard the weights such that the smallest one is always here. We just do the multiplication with the first 16 neuron output, and then we do the 32, and then we do this.
Oh, I see. So you don't have dropout like separately. It's just an implementation.
Yeah, it's like the first implementation we did was a masking implementation, so that is the closest to dropout. The second one we slice the weights and we do it. Okay, cool. So if anyone wants to go through more things, you can actually fit a router on top of this so that easier tokens are passed to a smaller model, as you said. NVIDIA has a couple of very nice papers. They also figure out a model to cater to your explicit downstream needs. So if you say that I want a latency of 3 milliseconds, they'll find a model. So it's real architecture search without training. Good. So last thing is, so that was Matryoshka transformer, short form transformer. And having looked at like vector representations and transformer, for some reason, like Jeff Dean once comes to us and says, hey, can you do this in integer data types? Right? Yeah, that makes sense. An 8-bit integer, when you look at it, the first 4 bits should be the 4-bit integer. If you're 8-bit quantized model, if you take the first 4 bits, it's not a 4-bit integer, then something is wrong. And if the first 2 bits are not 2-bit integer for your into model, something is wrong. And what does this remind you of? It's the Matryoshka law. So you do an 8-bit quantization with QAT. You also want to do 4-bit and 2-bit. Currently, you do all of them separately. And yeah, and then 8-bit and 4-bit, even without QAT, are pretty good. You don't need to do anything, but 2-bit is pretty bad. So it turns out the baselines are pretty good, like except for the 2-bit, like you get about 60% task average. 3-bit is nearly optimal, is what Tim Detmers and co showed at some point in time. 3-bit is pretty good. That's the 3-bit model. But anything below 4-bit, then you do without training, without QAT, which is just min-max quantization or something, it just falls off. And slicing is even bad. Like if you just take a quantized 8-bit model, slice the first 2 bits, first 3 bits, first 4 bits, it's pretty bad. It just falls off. But just notice that the 4-bit is pretty good at any point in time. Just the lower precision. So as with all the things we talked today, that's pretty much it. So you have a model, you quantize it to 8 bits, slice off the first 4 bits, compute loss, slice off the 2 bits, compute loss. And it turns out this gives Pareto optimal for everything within 3 bits, and it gives a boost into the 2 bit, similar to what we saw in Matryoshka, about 3%. And what is happening here is if you look at the distributions, it's kind of sacrificing accuracy of 8-bit to push the values of 2-bit to the right side. So if you don't do mad quant or Matryoshka quantization, the distribution of 2 bits is shifted a bit leftward, so it's not using the higher precision values. Okay. So a simplest way of thinking about it is it doesn't matter to the 8-bit model if the value of the weight is 64 or 65, but it matters a lot to the 2-bit model if the value of the weight is 1 or 2. So this is what we are trading on. So moving from 64 to 65 will flip a bit, which will affect 2-bit a lot more than 8-bit. And it turns out the models start realizing that very, very quickly. and push things such that into starts becoming better because intent is so parameterized that they can flip some bits and it'll be okay. And yeah, mix and match works here. So first layer can be 2-bit, second layer can be 3-bit, 4-bit, whatever. This works really, really well. However, if you notice here, it is not Pareto optimal. 3-bit is slightly above. And this 3-bit is a sliced 3-bit. So we trained an 8-bit quantized model with matplotlib with 8, 4, and 2, and sliced off the first 3 bits. It's as good as a 3-bit model, but the mix and match models are nowhere close to being as good as a 3-bit. So this is something we noticed and we fixed it by accident. So what happened is we forgot to clip the 2-bit model to the value of 4. So if you forget to clip in a quantization, the value overflows to 5. So about 2 to 5% of the weights, when they go to the extra bucket, fix all of the stuff you are looking at, and it becomes very powerful. So these are the outliers. So the entire thing, like LLM.intake paper, like they talk about outliers and like storing them in higher precisions. Those are the things which are being captured indirectly and being put in a higher bucket. It is just 2 to 5%, which raises your 2-bit effective bit rate from 2 to 2.05. And it improves your accuracy by like 3 to 5%. Okay. So yeah, and it's all Pareto optimal. It's about total 8% improvement. So it was 3% and then 5 on top of it. We have a couple more tricks. Code distillation from int8 because int8 and int2 are in the same space. Getting logics from int8 and training int2 is much better rather than just training from ground truth. So that helps. Like if you don't have it, you lose 4%. So adding that like gives you that 4% boost. So initial 3% was because we had a drop and then code distillation helped it and it pushed it beyond. So the total gain is about 8% at this point. And yeah, and we also found something on accident called so all of these quantization techniques usually emulate for the NLP or FFN weights. Attention you do not touch because attention is a bit more sensitive to all of these precision problems. So we started training a QAD run for 2-bit, started like failing, we didn't know what was happening. And then we invented something called single precision match. So it literally is matquad, but zero out the weights of 4-bit and 8-bit. So technically you're optimizing for three losses, but the last 2 losses are completely gone. What it means is you're over parameterizing the 2-bit as an 8-bit, slicing off the 2 bits and then optimizing. So now the 2-bit can flip bits such that the extra noise can go into the other stuff and the other stuff doesn't. Okay. So the 4-bit and 8-bit accuracies tank after that. Like we are not going to like look at them, they're not going to be anywhere good. But the 2-bit accuracy just like shoots. So just having this extra entropy of additional bits is literally over parameterization. You study all of what pulling literature has told us. Adding this extra parameter just helps us like improve a lot of trade. If something is destabilizing this, is going to performance. So then an interesting thing we wanted to do was extend this to FP8 and FP4. FP4 can be a nest of FP8. Turns out it's extremely hard because integers are linear in scaling. So if you go from 4 bits to 8 bits, it's multiplication by 2 to the power of 4. If you go from 4 bits to 8 bits in FP, it's 2 to the power of 2 to the power of 4. So it's exponential. And doing the slicing business in exponential space, whenever you get a gradient, is exponential in loss. So you need to stabilize this. You need to figure out the right gradient optimization to make FP4 nest within FP8. This is a very, very interesting problem because NVIDIA's chips support FP4 and FP8. And if you can leverage FP4 for most of the stuff and only compute FP8 when you need it, that's going to be extremely faster than inference. And of course, you can always train routers the same way. For easier tokens, you just fetch 2 bits for harder tokens. Anyway, at a high level, the takeaways are, this is a very simple technique. It generalizes extremely well. I have rarely seen a simple fundamental block which was not affected by this, and it just works really well. It scales to like billions, if not trillions of documents. Elasticity and adaptivity will be crucial and are already deployed in real world AI. So as academics, I think we also benefit from a multiple plan of models coming from one single shot, and you can study them a lot better with one training. It's just simple, it works, scalable, slow and user. Thank you. Okay, happy to take questions. It's actually as simple as it looks. Like people ask me if there are any tricks, there are no tricks. It's actually as simple as it.
I guess maybe in terms of, say, modularity or something like that, where you are able to focus, because say, when you do this training, you mentioned that in the first 16 dimensions, like some of these maybe more core, simpler capabilities can be encoded, and then you need, in the rest, it's like, I don't know, has there been work on incentivizing specifically to concentrate a particular type of capability into, either the first 16 or it's less important, and so then as a result, like leave it for later dimensions or something like that, like by saying that like Matformer or something like that, by having inputs only of a certain data type only go into later things, or maybe only into the, something like that.
So that's a very good question. So the losses here currently consider them to be the same loss.
Yeah.
They can be completely different losses. No one is stopping you from using the same loss. So we have tried for Matryoshka representations, we tried classification loss for the highest dimensionality and like retrieval style losses, like Matryoshka loss. It kind of works fine. You can also subsample data, as you said, like only the easier things can go into this. And again, one thing I learned in last 7 years of my research career is adding any inductive bias is usually a bad idea. This is one thing which kind of works. And pushing it with more inductive bias probably is not worth it. We let the model figure out what it wants to do.
Yeah.
Makes sense. Yeah. Oh, so there are only four blue points here, right? You only trained for 4 of them. I want to span the entire Pareto curve. You just get that with mixed image. You never have to train any model. So during inference, let's say your iPhone is a 14 version instead of 16 is the latest one, right? I don't use it. So it only can support like maybe somewhere in between your largest and the middle size model, and you can afford that. But Llama released only like 2 models, like the largest one which goes on 16 and like the smallest one which is much cheaper than what can fit on 14. So you want to pick something in between which is maximum accuracy for your compute budget, and you can do it on the fly during inference. You don't have to train for this model by just sampling from this image. Okay.
Yeah, so going back to the setup where you had like 4 models here of size S, M, L, XL. Let's say these are language models, and so generally the loss, what we care about, we generally optimize for the size as well as the number of tokens the model sees, and that's those scaling laws, right?
Yeah.
Let's say if you were training a 70B, XL is 70B model, and your S is, let's say, 3B model, and your S is in some sense being trained on, let's say, 15 trillion tokens. Normally you wouldn't train a S that much, right?
That's a good question. So there are 2 parts to this question. The first one is 70 to 3 is stretching it too much. We usually are like, happy with like 70 to like in a hypothetical world, like 70 to like 10 is good, or like 15 is good. I'm just making up numbers, but yeah, that would be good. You don't want to have too small of a model which will destabilize the training. That goes back to point like someone raised. It's too thin of a model, it's too small of a model. Yes. Coming back to the question of training data. Yes, it's not optimal, but overtraining helps.
Yeah, sure.
So I mean, the whole thing is Llama 3 series was trained on the same token budget for all the models. You might as well just train all of them. Yeah.
So is this like the overflow phenomenon?
So here I'm doing the joint training, right? You can actually do sampling as well. When I say sampling, you can choose not to optimize this model for some of the batches as you put, because they're not optimal for it. It works really well. It also saves you some stuff. But yeah, usually like the most general purpose is this, and you can just like mass amount this stuff.
Yeah, is it sort of analogous to like the register tokens papers? Like
Yes, register tokens also talks about the same thing. Word parameterization lets your noise flow into that, so your optimization is easy. So more parameters is good.
Maybe.
Someone had a question.
Oh, yeah. Jay from online, can you pick up your question?
Yes. Hey Aditya. So my question is, can we use Matryoshka embeddings to compress long context and push that into a model? Like if a model that has capability of taking 128,000 token limit, can we compress a 1 million token limit using Matryoshka embedding and make it understand by the model and give back the answer?
I mean, you can probably Matryoshka KV cache such that your 1 million can be stored a bit cheaply. Or probably help you only pick the most important 128K. We haven't tried any of those things, so like, yeah, I mean, KV cache Matryoshka is something we don't have an idea about at this moment.
Okay. Thank you so much.
Awesome. So I think we are about time. So let's just thank our speaker once again.
I'll be around for next couple of hours.
Yeah.
Keep it there.